You know, in the world of high-tech manufacturing, especially something like pharmaceuticals, water isn't just, well, water. It's a precision-engineered raw material. Honestly, a single drop of it can be way more critical than a barrel of oil. But what happens when that supercritical ingredient is needed everywhere in the facility, all at the exact same time? I want you to picture it. Every single valve, every nozzle, every piece of equipment in a massive, sprawling facility, they all open at once. It's the kind of scenario that keeps plant engineers staring at the ceiling at 3 a.m. Why? Because if the system isn't built for that one exact moment, the result is, well, it's catastrophic failure. There's a name for this exact scenario, a peak load event. You can think of it as the ultimate stress test for a multi-million-dollar operation. It's this sudden, absolutely massive spike in demand that can bring the entire system to its knees. So how on earth do engineers actually prepare for this daily Black Friday sale? Okay, so let's really dive into this. We're talking about a moment of maximum demand that can literally make or break a production batch that's worth millions. This is so much more than just a rush hour. It's a high-stakes engineering puzzle with everything on the line. That analogy really nails it, doesn't it? It all comes down to pressure and flow. When that demand suddenly spikes, the pressure in the system can just plummet, and the result is exactly like that music festival nightmare. Everything down the line just stops. The whole operation just chokes. And here's the kicker. This isn't some rare, once-a-year thing. In a big pharmaceutical plant, this peak load is a daily reality. And if the purified water system can't handle it, production grinds to a dead stop, costing a fortune and putting entire product lines in jeopardy. So how in the world do you prevent this kind of system-wide meltdown? Well, you definitely don't guess, you test. And this is where something called a peak load study comes in. Think of it like putting the system's heart on a monitor while it's running a marathon. Okay, so let's put it this way. A purified water system is kind of like a city's power grid. A peak load study? That's like turning on every single light, every TV, and every factory in the entire city all at once, just to make sure the grid doesn't completely collapse. It's a deliberate, totally controlled stress test to find the system's breaking point before it finds it on its own. Now, this study has a few really critical goals. For sure, it proves you can keep the water flowing and the pressure up everywhere. But maybe even more importantly, it's about preventing the growth of biofilm. That's a dangerous, slimy layer of bacteria that can contaminate absolutely everything. And of course, it satisfies the regulatory agencies like the FDA, who demand proof that your system actually works under the absolute worst-case conditions. And this right here is the fundamental reason why flow is everything. When that water flow drops and the water becomes stagnant, bacteria can literally stick to the pipe walls and form that nasty biofilm, which can ruin your entire system. But turbulent, high-velocity flow, that acts like a pressure washer inside the pipes, constantly scouring them clean and making sure the water stays pure. I mean, one leads to a total shutdown, the other leads to safe, consistent operation. It's that simple. All right, so we've covered the what's and the why. Now let's get into the engineering battle plan. How exactly do you design a system that can take this kind of daily beating without going totally broke in the process? Engineers are smart. They know that not every single tap is going to be open 24/7. So they use something called a diversity factor, which is basically a calculated guess of how many points will be active at once. It's kind of like how a city planner knows not everyone is going to be driving at the exact same second. This lets them design a system that's tough enough for the peak, but not ridiculously wastefully overbuilt. So to get that pipe scouring, turbulent flow we were talking about, engineers aim for a very specific speed for the water, somewhere right between 3 and 6 feet per second. That's the magic number. If you fall below it, bacteria can get a foothold. If you go too far above it, you risk wearing out your pipes and just wasting energy. It is a precisely calculated sweet spot for a clean, efficient system. But look, a strong design is only half the battle. The system also has to be smart. It needs to react in milliseconds to sudden changes. And this is where the system's digital brain comes into play. So the whole system really relies on 3 key pieces of tech. You've got VFDs, or variable frequency drives. Think of them as the pump's gas pedal. They can speed it up or slow it down instantly. Then you have back pressure valves, which act like traffic cops, making sure pressure stays steady. And finally, the PLC, the programmable logic controller. That's the digital brain of the whole operation, monitoring everything and making split-second decisions. Okay, so here's how it all works in literally a fraction of a second. A couple of big valves open up and the system pressure starts to dip. The sensors detect this change instantly and shoot an alert to the PLC. The PLC brain then tells the VFD to floor it, to ramp up the pump speed, restoring the pressure before anyone or anything even has a chance to notice. It's a totally seamless automated defense mechanism. So let's pull all of this together. Why go through all this insane trouble for a water system? Well, because when you're making life-saving medicine, the stakes just couldn't be any higher. I think this says it all, really. You could have the most brilliant drug formula on the planet, but it's completely useless if the water you use to make it is contaminated, or worse, just not available. At the end of the day, the water system isn't just another utility, it's a foundational pillar of the entire manufacturing process. And if that pillar crumbles, the consequences are just severe. We are talking about product contamination, losing entire batches worth millions and millions of dollars, a complete facility shutdown, and massive fines from regulatory bodies. So a peak load study isn't just some nice-to-have test. It's an absolutely essential insurance policy for the facility's financial health, its reputation, and its future. Ultimately, when you're dealing with high-stakes engineering like this, preparing for the worst-case scenario isn't really about expecting failure. It's about guaranteeing it never, ever happens. Which makes me curious, especially for those of you in the industry, what's the biggest system crash you've ever seen? I'd love to hear those stories.